Hi, I'm Yue from the University of Tokyo, and this work is a collaboration with Alaya and Microsoft Research. In this work, we propose the Associative Transformer. It's building upon the recent neuroscience studies of the Global Workspace Theory and Associative Memory. So let's start with background about the inductive biases, since it's the main problem we are considering in this research. So inductive biases enable the effective capturing of input data structure, such as if you consider convolution operations. So it's the 10 to different parts of the images. So it's important to guide the model to generalize effectively within the underlying data distribution. By control, the vision transformer models that rely on the pairwise attention are usually considered without such an inductive bias, making them less efficient when handling more complex samples. Studies of sparse attention mechanisms in transformers leverage the computation among patches of input images to naturally derive the spatialized pairs as inductive biases. So these blended pairs contribute to the efficient association of information fragments in the input. And besides the benefit of efficiently learning localized and contextual relationship between different representations, such a bottleneck of the information can also reduce the computation cost compared to the pairwise self-attention. So first, similar to the Ramsell's paper on the Hopfield layers, we performed the evaluation on the sparsity of attention heads in a pre-trained vision transformer. Our analysis of the attention heads reviewed the different sparsity across different attention layers. And usually the middle layer showing the notable degree of sparsity compared to the lower and higher layers. So the result aligns with the study on the NLP task. We found that the computation which revealed the naturally sparser interactions among the attention heads in the pairwise attention is important for learning meaningful representations. And our goal here is to introduce such computation by learning a set of pairs that can guide the attention in the learning process. So how to achieve that? A more broader concept we considered in this study is the attention we are considered can find the resonance with the neuroscientific grounding. It's called the Global Workspace Theory. And OGWT, the GWT explains the cognitive architecture we usually use to guide our attention when we are thinking and try to solve a problem. So there's a limited capacity of such a global workspace. It allows only a few of these competing modules to enter each time, depending on the contextual information. So it's quite similar to the top K computation, maybe some of you mentioned in your talk. Then the information entering the workspace will be made available for the other modules to update their states. An example of this direction is the coordination method. And in this method, they use the cross attention to sparsely select the patches instead of use the dense attention, so that only a few of them can enter the space to update the states. So this is the basic conceptual idea of our proposal. It consists of 3 parts. The first component is we want to collect all the valuable patches from the current batch. So it's different from the batch processing. We want to observe all the valuable patches at the same time instead of process the patches for different samples. So we think it's more nature, so how we observe the environment. So in the graph on the left-hand side, you can see the images are represented by different hues, and the patches from the same images are distinguished by different brightness. And the squash layer here try to concatenate the patches from different batch samples and send to the next component. So this component, you try to compute the bottleneck attention and select the different patches. To achieve that, the output of the squash layer is attended by the cross attention using the current explicit memory, so it can be initialized depending the designs. And the output of the cross attention is then used to update the current memory so that more meaningful patches can be selected. And the update of the memory can also be further processed and smoothed by the method like exponential moving average, and also constrained by the additional rules like the bottleneck attention balance rules we propose to enable the diverse selection of patches and also the slower forgetting of the older knowledge. And here I show some of the examples of the selected patches by the learned pairs. We can observe a noticeable increase in the diversity of the selected image patches with learning progresses. And the final component is the learned pairs in the updated explicit memory. The gamma T plus 1 can also be leveraged by a continuous Hopfield network as different attractors. But instead of fixed attractors, we consider it's a set of learnable attractors to reconstruct the input samples. So the Hopfield network can then iteratively decrease the energy of a sample with respect to the explicit memory, which is learned through the training, to enable the retrieval of knowledge within the memory. So in the upper graph, we show the energy of the reconstructed patterns over the batch time steps for a two-layer associative transformer. So it shows it's kind of overfitting at the last time step, but generally it can decrease the energy of the samples. And in the lower graphs, we show the Hopfield networks fine-tuning based on the inverse temperature parameter beta. And as shown in the peer studies, when we adjust the beta, the distribution of the attractors can be very different. And usually a smaller beta is more likely to result in a meta-stable state within the Bayesian of the multiple attractors. And the graph on the lower right-hand side shows that very large or small beta both can lead to some local minima here with identical patches retrieved from the memory. So the heat maps here show a specific sample, and as you can see, the different patches inside the sample are, if the beta is too low or too high, they are all reconstructed to the same patterns from the memory. And so we call this the associative memory augmented attention layer, the global workspace layer, and the enhanced transformer architecture, the associative transformer. The proposed global workspace layer, you can consider it can be used as an add-on component integrated in the conventional transformer model, and I will mention what's the benefits we need the actual layer for it. I show here the different patches across samples are attended sparsely by different pairs, and each pair usually attend to a specific areas across different samples. Here shows the evaluation on the image classification tasks such as cipher and triangle data sets, and it shows that the proposed method can outperform the latent memory-based transformers, such as the state-of-the-art coordination and perceiver models, at the same time requiring a smaller or comparable model size. So you might be wondering why we need additional layers. So the reason is the proposed AIT is a layer-efficient model. If we train a vision transformer, it needs 12 layers. But we can use a smaller model with only 6 layers to outperform the vision transformer, even with less model parameters. And the final result is about addressing the relational reasoning tasks, such as the visual question answering task here. The AIT shows better performance and even achieving competitive performance with the upper bound method we considered, which is the non-transformer-based models. So it usually relies on the strong inductive biases by design, so it's usually outperforms the transformers. To conclude, we propose the associative transformer. It's a biologically possible sparse attention mechanism based on the global workspace theory and associative memory. And AIT is sparse representation learner, leveraging the bottleneck attention to acquire specialized pairs. And the adaptive, it's a low rank pairs, and it can increase the memory capacity. So AIT can learn up to 128 specialized pairs at the current point, and it can select from a diverse pool of more than 32K patches. And the final point is the learned pairs can also serve as attractors in a Hopfield network. And it's the first work to incorporate the Hopfield network as an integral element in a sparse attention for the inductive bias problem. Okay, so yeah, please refer to our paper for more details. I'll come to the poster. Thank you very much.